We're starting at 16 now, section 16.3, which is a rotation about a fixed axis. And we're going to see a lot of the equations that we saw previously, except previously we had them for linear applications. Now we have angular rotation. So, we might have something, like some kind of a disk, say, moving, say, clockwise or maybe counterclockwise with something like this. And say theta would be the angular displacement. And omega is the angular velocity. And alpha is the angular acceleration. And of course, similar to before, we had our basic relationships that omega is going to be d theta dt. Or if we rearrange this, this would be d theta equals omega dt. And also we had alpha was equal to d omega dt. Or if we rewrite this, this could be d omega is equal to alpha dt, like this. And so those are just the basic relationships from the derivative, just we actually had done this a little bit previously, that of course, if you have like the change in, say, the distance, the derivative of that's always going to be the velocity, and this is just with angular terms. Same thing, the acceleration is equal to the derivative of the velocity, except with angles. And just like before, you remember we had x equals x naught plus alpha t. We have similar relationship with angular accelerations and velocities. And if the acceleration is constant, for say constant acceleration, we're going to have omega equal omega naught plus alpha. And like the book, just to use a book notation, sometimes if they have a constant acceleration, they'll put a little c down here just to emphasize that. You don't have to do that, but just keep in mind, this only applies when the acceleration is constant. And so this, again, this is similar to, okay, this one would be like velocity equals initial velocity plus acceleration times, except just it's with angular stuff now. And same thing as before, position, remember, was equal to x naught plus the velocity times t plus 1/2 at squared. So we have the same thing here. Theta is equal to theta naught plus omega t plus 1/2 alpha c t squared. And also another relationship we had that we use once in a while with was using velocities. And so we have a similar relationship with angular velocities. If we want the angular velocity squared at any time is equal to this. Again, this would be the case if we don't know anything about time. We just have everything in terms of angles. And then, of course, from before, we also had in the last section, I believe, we had, if you have something, say, turning at some speed omega and at some radius r, the tangential velocity v of t is like this, and then the velocity is always equal to omega r, like that. And in vector form, which we're going to use once in a while, we're going to have this. I think the book puts a p down here, but this is the same thing in vector form. And then where this rp is measured from any point on the axis of rotation to the point P. And maybe let me put in the P in the picture, may put the P like right there to the point P, like that. And we're going to have some things that we had previously, of course. The tangential acceleration is going to be equal to alpha times r. Once again, you know, if you have a disk or something like this, the tan A of t going to be omega like this. And then something you've used lots of times is the normal acceleration is velocity divided by rho. And then now if rho is just radius, if it's just like something circular, then we can write this way. You know, if rho is just the radius, put that down. And then also, since the velocity is equal to omega r, then this will cancel. So this ends up being omega squared r. So if we know omega, we can find the normal acceleration this way. And now let's consider, say, two things that are meshed together, maybe two gears or something, one is turning the other. Let's say if you have, whenever you have two rotating bodies in contact, so let's say you have a picture like this. Something like this. And so let's say that you have some contact point here. And say the point A right here. So if you have, again, two things spinning like this, the velocities of each disk will be the same. And the tangential accelerations will be the same. So again, this would be like maybe two gears, one turning the other, and that's going to be true. And so let's go through some of this. Let's take an example. This is just sort of preliminary stuff before we actually get to the problems. Let's take a look at something like this. So let's say you have two disks. Say this is a 3-foot radius. Say this is disk A. And omega A is 5 radians a second. And then you have disk B. And again, 1-foot radius. And it's moving at some velocity omega B, like this. So let's ask some questions. What is the velocity of the rim of A? What is the angular velocity of B? If A rotates 6 radians, how much will B rotate? And if B rotates 2 revolutions, how much will A rotate? So those are the questions. Let's take a look at this. Solution A. And so we said that the velocities are going to be the same for both disks. And also for A, we know its radius and we know the angular velocity, so that's going to be pretty simple. So VA is going to be the angular acceleration of A times the radius of A, which is 5 times 3, which is 15 feet per second. And also, that's, as we said in the previous page, also the velocity of B is going to be the same. It's going to be 15 feet per second. And then number B, what is the angular velocity of B? So we know that VA has to be equal to VB. And again, that means that the angular velocity of A times R of A is the angular acceleration of B times R of B. This. And if we just put in the numbers, then we have 5 and 3 equals WB times 1. And if you work that out, you get WB is equal to, or omega B is equal to 15 radians per second. And for part C, it's similar relationship. Let's see, if we're told it rotates that many radians, I guess that we could put this in terms of angle. So, so really like the lengths that they map out are going to be the same. So in other words, we can say theta A RA is going to be equal to theta B RB. And so if A turns 6 radians and its radius was 3 feet, then we multiply theta B times its radius, and that's going to be theta B is 18 radians. And finally, on the last one, pretty much the same thing. You could really do that in terms of radians if you want to convert it, but like say the 2 pi's would cancel out. So we can really do it the same way. You can just say, just use this relationship here. And this is going to be 3 feet. Theta B, we said there's 2 revolutions times 1 foot. So theta A comes out to be 2/3 revolutions. Like this. Any questions on any of that? Good.
I have 2 questions, but the first one might be a little better. But you specified that the velocity, we were looking for the velocity day at the rim. I'm assuming it's going to be different depending on where you are at the disk.
Yes, right. Yes, exactly. Yes, that's right. This would be, that's a good point. Right. So this is at the rim, right? And then therefore, if we would have been, say, so that would have been anywhere here, then of course, yes, if we would have been, say, at maybe 1.5 feet from the center, then we would have had to change this to 1.5. That's right. That's right. Is that what you're asking?
Yeah.
Yeah, exactly. Right. Yes, the velocity, it would be like, say, the linear velocity, therefore it's based on what radius that you're at. So therefore, like, so let's say if we go down, so like here, this is saying it's the angular velocity times the radius. So actually, like a point real close to the center here is going to actually be moving pretty slowly, huh? So it's going to be moving a lot more slowly than is on the outer, than same with the outer rim would be. That's right. Right. So yeah, so it depends upon uh, the radius. That's right. Does that answer your question?
Yeah.
And do you say you had a second question?
Yeah, for the last two parts, you said that the theta of A times the radius of A is equal to the theta of B times the radius of B. How, like, could you maybe explain that a little?
Oh, yes, right. Yeah. So let's see. So if we did that, so what's going to happen? Let me see if I say this correctly. So that's going to be, uh, and maybe it's best to see like in terms of circumference. Let's say if we did, so let's say if we do one like this, so you have like, say, a radius here, say call this radius A. And let's say we have radius B. So then let's see if this is turning. So this is going to turn, so this one is going to turn, say for one revolution. Let me see, am I saying that right? So the total length for A is going to be equal to total length of B. In other words, I guess what I mean to say is that the circumference, like say the circumference that's mapped out at A is going to be equal to the circumference mapped out B. So in other words, it'd be 2 pi RA times the number of revolutions. And so, yeah, let's do it that way first. Or yeah, let me do it in radians first. So times theta A is going to be equal to 2 pi R B times theta B. So in other words, the same amount of length that, say this point A, so let's pick a point, let's pick a point P over here. Pick a point P here, and let's say make it the same point on P on this one. So the amount of length, that's probably a better way to say that. So let's say if you have a point P here and a point P here, and the total length traveled by the point P on A is going to be equal to the total length traveled on the point P of B, if that makes sense. So in other words, so in the point, the total amount, so in other words, as this is turning, this is going to, so the point on P will travel the same distance on A as it does on B. And that's going to be like, say, 2 pi R. So for each revolution, for example, that it's going to turn would be 2 pi R. So again, if this is, say, the number of revolutions, and say this is the number of revolutions. So this, let's say if this is going to travel, say, 20 inches here, the point P on this one will also travel 20 inches. And so that's going to be 2 pi R times the number of revolutions. And for B, it's going to be 2 pi r times the number of revolutions. Of course, the 2 pi's cancel out, so it'll be RA theta RB theta like that. Does that make sense at all? In other words, what I'm sort of saying is that linear distance that P moves on A will be equal to the linear distance that P moves on B. Does that make sense, everyone? Am I saying that right? Does that sound right there? Okay. I wasn't sure if I was saying it right or not. Yeah, so that's what's going to be equal. So and that's good. So the linear distance that's going to move is going to be 2 pi r times the number of revolutions, like that. And or if it's if you don't have the number of revolutions, then it's actually just going to be r times theta equals r times theta. Is there any questions on that? Okay, good. Any other questions on anything on that? Good. Yeah, these are sort of some basic things. So yeah, kind of go over those. These are kind of some basic things we'll need when we do the problems. And the other thing that comes up a lot is having to do with belts. So let's say if you have a belt that's turning between one pulley and another pulley like this. So let's say if you had something going around like this here. And once again, let's say if you have over here, let's say this is A this time. And let's say its radius is 2 meters. And you have this over here, B, and its radius is 8 meters, like this. And so let's take a look at some examples. So now what's going to happen is the belt velocity is always going to be the same. You see, so say the belt velocity. And so let's say you have the velocity of the belt is 12 meters per second. And the acceleration is 5 meters per second squared, like this. And so the belt's going to be moving along between these two. So you can see what's going to happen is that's going to force the velocity of disk A to be 12 meters per second and the velocity of disk B to be 12 meters per second. And so the question is, what is the angular velocity of A and B? And what is the angular acceleration of A and B? And so let's take a look at that. And so once again, it's like we said before, this belt's going to be moving the same all the way around, which is going to force the velocity of the outer rim of A to be 12 meters per second and the outer rim of B to be 12 meters per second. So we can say that velocity of the belt velocity is going to be equal to the velocity of A, that's of the outer rim. Let me just note that that'd be for the outer rim of A. So therefore, this velocity is, again, this is say the belt velocity. And that's as well going to be equal to the angular velocity of A times the radius of A. That's be 12 WA times the radius of A is 2. and omega A is 6 radians per second. And same thing with, similar thing with B, if your velocity of belt is equal to velocity of the, again, of the outer rim of B. And so the velocity of belt is equal to omega B times RB, which is 12, omega B 8. And if you solve for omega B, that's 1.5 radians per second. Any questions on that? Questions at all? Main idea is the belt, is always going to go the same velocity as the outer rim. And again, when you kind of see these are all pretty logical, but it's easy. The reason in the past, it's easy for people to make mistakes on these. So I want to be sure to go over these. And so same thing, acceleration, it'll be the same thing. Acceleration of the belt is going to be equal to the acceleration of the outer rim. And that's going to be alpha A R A, be 5 equal alpha A times 2. Alpha A is 5/2 radians per second squared. And same thing for B, belt acceleration of B is going to be, again, just same as before, alpha B or B. 5 is equal to alpha B times 8. Alpha B is like 5/8 radian per second squared. We're going to take a look at this problem, F-16-1, F-16-1. And it says when the gear rotates 20 revolutions, it achieves an angular velocity of 30 radians per second, starting from rest. Determine the constant angular acceleration and the time required. So notice here that the angular acceleration is constant. That's going to be really important because we'll be able to use those basic equations if the angular acceleration is constant. So always look for that. In this case, it is, so we can use our basic equations. And also here it says we're starting from rest. Keep that in mind when we're setting the problem up. One. And again, starting from rest, so omega naught 0. And so therefore, and also we call our starting position 0. And 20 revolutions is going to be equal to 20 times 2 pi radians, or 40 pi radians. And so you can say that your final theta is going to be 40 pi. Like I said, since it doesn't say anything about time, that'll give, and since the acceleration is constant, let me say this, alpha is constant. So you want to use omega squared, omega naught squared plus 2 alpha times theta minus theta naught. And so we want to know, starting from rest, determine angular acceleration time required to get to 30 radians per second. So 30 squared is 0 squared plus 2 alpha. And we have 40 pi minus 0. If you put that on your calculator, we get 3.58 radians per second squared, like that. And so now it wants to know how long it takes to get to that acceleration or to that velocity. Then we can just use the other equation we had. Remember, this was omega naught plus alpha t. And so we had 30 radians per second. We're starting from rest. And we just found our acceleration 3.58 t. T is 8.378 seconds.
Next, we're going to look at this problem, F16-2. F16-2, it says the flywheel rotates with an angular velocity of 0.005 theta squared radians per second, where theta is in radians. Determine the angular acceleration when it is rotated 20 revolutions. So again, in this problem, obviously the angular acceleration is not constant because you can see the angular velocity has a theta squared. So if we were to take the derivative of that, we'd still have a theta in there. So the angular acceleration is not constant. So we won't be able to use the very basic equations.
F16-2, we'll use theta d theta is equal to omega d omega, like this. And then we can rewrite this as alpha equals omega d theta. And then we're given our omega, aren't we? We're given that that is going to be 0.005 theta squared. So we're going to have to take the derivative of that, huh? So if we do 0.005 theta squared, then we need d omega d theta. So we'll have to take the derivative of this, huh? So if we just bring the two forward, right? So if we do the derivative of this right here, derivative of omega, that's going to be 2 times 0.005 theta, like that. And so if we put that together a little bit, that'll give us 0.00005 theta cubed. And let's see, we're told for 20 revolutions, huh? Let's see, we're told, yeah, 20 revolutions. So that's going to be 20 times 2 pi. So we can put that in for a theta. And remember where that came from, that's 20 revolutions. Like that. And put that on your calculator, you get 99.22 radians per second squared. Like that.
Next, we're going to look at this problem, 16-2. 16-2, the angular acceleration of the disk is defined by alpha equals 3t squared plus 12 radians per second. Actually, I think that's a misprint. I think it should say radians per second squared. Yeah, I think that alpha should be radians per second squared, where t is in seconds. If the disk is originally rotating at omega naught equal 12 radians per second, determine the magnitude of velocity and the n, which is the normal, and the t tangential components of acceleration of point A on the disk when t is 2 seconds.
Five meters like this. And we're going at initially at 12 radians per second. And so we have our radius, we know what our radius is. Again, alpha is not constant. It is 3t squared plus 12. So we could probably use our dw dt is going to be our acceleration, huh? Because acceleration is the derivative of velocity. And so omega is the angular velocity, so we can use this. And so we'll rewrite this as dw and put the alpha in here. So that's be 3t squared plus 12 dt, like this. And we can integrate from zero, well, actually from 0 to t on the time, but now our original angular velocity is going to be 12 radians per second, so go 12 to omega, like that. And then integrate both sides, we get omega 12 to omega. Integrate this is t cubed plus 12, 0 to t. Again, I'm sort of doing integration the way the book usually does. If you like to not put the bounds on and do integrate it and just get your C and evaluate that way, that's fine as well. That's why I usually do it, but I'm just doing in this class not the way the book does it. So minus 12, and then put the upper bounds minus the lower bound, we get this. So our omega is t cubed plus 12t plus 12, like this. And then find what happens at t equal 2 seconds. And that's 44 radians per second. Like this. So again, all I did was just plug things in. And we know what the acceleration is. It's 3t squared. So we can just put that in here. And that gives us 24 radians per second squared. So now once we have that, we can just use our basic stuff. Velocity equals omega r, which is 44 times 0.5, which would be 22 meters per second. And tangential acceleration is alpha r is 24, 0.5 per second squared. And an is omega squared r 44 squared, like this, 968 meters per second squared, like that.
Next, we're gonna look at this problem 16-10. 16-10. It says at the instant the velocity is 5 radians per second, pulley A is given a constant angular acceleration of 6 radians per second squared. Determine the magnitude of acceleration of point B on pulley C when A rotates 2 revolutions. Pulley C has an inner hub which is fixed to the outer one and turns with it.
Couple of pulleys like this, and we have a belt going from here to here, and from here to here. And this one is 0.5 meter radius. And this inside one here is 0.04. Actually, this first one's wrong. That's 0.05. So radius. And then this radius here is 0.04. And then this one here, the radius is 0.06. And there's a point B out here. Call that B right there. And this is our disk A up here. And again, so there's a smaller hub connected to the pulley. These are connected together. And we're going to need to find the velocity of point B and find the acceleration of point B. And so again, we want to know this, these values after A rotates 2 revolutions. Again, we're given in terms of revolutions rather than in terms of time. And then so remember, of course, like 2 revolutions equals 2 times 2 pi radians. So let's see what happens then. So pulley A. So again, we know more stuff about pulley A, so we'll start with it. Pulley A after 2 revolutions. Again, which is going to be 4 pi radians. So we have omega squared equals omega naught squared plus 2 alpha theta minus theta naught. And now initially it's moving at 5 radians per second. Pulley A is 5 radians per second, so put that in here. And then the initial acceleration, I should write these up here. So initially this is going to be 5 radians per second, and alpha A is 6 radians per second squared. So we can just substitute those values into our equation. 4 pi, and you can assume like it's starting at theta 0. So we have this. Fix that a little bit. And when you calculate all this out, we get our omega is going to be 13.26 radians per second. Again, this is the angular velocity of A. After 2 revolutions. And so the velocity of the belt remember, just going to be simply the radius of A times the angular velocity of A. And that's going to be our 13.26 times the radius of A was 0.05. That's going to give us about 0.663 meters per second. That's the velocity of the belt. So once we know the velocity of the belt, we then can go look at pulley C, because the belt goes from around A to C. Remember, the belt is always going to have the same velocity all the way around. So that means when it's at C, it's going to have the same velocity there. So we can say, so at C, you have, say, something like this. Again, we said this is 0.04 radians. Move that up a little bit. And then we knew the velocity of the belt. The belt's going around this way. We said the velocity of the belt was 0.663 meters per second. So again, so we can just solve this using the information at C. So at C, again, same velocity of the belt. It's going to be the omega of C times the radius of C. And so that's going to be 0.663. Omega C, we don't know. And the radius is 0.4 meters. So the angular velocity at C is going to be about 16.6 radians per second. And so now keep in mind, this hub C is within B. So again, this is C, and think of C's over here. And then this point B is like out here. Let me slide this up a little bit. So this is our point B. This is C. So C is like in here. So whatever angular velocity C is, since it's directly attached to B, it's going to be the same. So they're going to be moving together. So let me just write that down. Angular velocity of C equals angular velocity of B. I call it B, but this is at least this point, so the whole disk is going to be moving at that same angular velocity. So in other words, we have WC, omega C equals omega B. And so that would mean that omega B, this was a 16.6, is going to be equal. Then for B, of course, so it's going to be 16.6. I guess I didn't need to say that. So the velocity of B, of point B, is going to be the omega B times the radius of B. And so the velocity of B is going to be 16.6. And the radius of B, would we say, was 0.06 meters. So the velocity of B is simply 0.995 meters per second, like that. So that was the answer to our first part of our problem. Now we have to find the acceleration of B. And so we have to go back to A and look at acceleration. So for acceleration, so look at pulley A. And so the tangential velocity of, let's look at, say, at the belt, let's say the velocity of the belt let me put this way, the velocity of the belt, sorry, uh, how do I say this? The acceleration of the belt is going to be equal to the tangential acceleration of A. Because if you think of the picture we have, like, so we have A up here, and this belt is moving around like this. So this, it's going to be around the outer edge. So the tangential acceleration of the belt is going to be the tangential acceleration of A. And then, so that's going to mean that the tangential acceleration of the belt is going to be alpha A times the radius of A, like this. So this is equal to that. Then just plug in the numbers. And that's going to be 6 times 0.05 is going to be 0.3 meters per second. So we have the velocity of the belt. So that allows us to give us some information for C. So we go to C then. Remember, it's the belt is going around A and C. So acceleration of the belt here is 0.03 meters per second. Then we can use that to find, so acceleration of the belt is going to be equal to the tangential acceleration of C. Then, of course, the tangential acceleration of C is simply going to be the alpha C times the radius of C. And we said that this is equal to this, so we can put 0.03, and then alpha C times the radius of C, 0.4. Alpha C then is going to be 7.5 radians per second. So once again, we know the angular acceleration, and since C and B are connected together, the angular acceleration of B is going to be equal to the angular acceleration of C. And so that means that if we want to find the tangential acceleration of B, that's going to be equal to the angular acceleration of B times the radius of B. And so ATB, again, since these are the alpha A, alpha B and alpha C are the same, 7.5 times 0.6, that's about 0.45 meters per second squared. Now, looking in the back of the book, it looks like they want the total velocity at B. So we have to find the normal acceleration B. A and B should be velocity B squared over rho 0.995 squared. And then this is going to be divided 0.06. Yeah, thank you. So this should be 0.995 squared divided by 0.06. Yeah, because that to be 16.5. So that one, that part was right. And then our total acceleration is still going to be the same as I showed before, 0.45 squared plus 16.5 squared is going to be 16.5 meters per second. Yeah, thank you. Yeah, thank you. So if you, those last two lines make this, so I'll show you what I'd written up when I did it at home. This is the way I calculated. So this is like the old, I know I confused the issue. So what I'd written on my paper here, I had done AN was equal to velocity squared over rho, but this is going to be equal to omega b squared times RB squared divided by RB. And then this, so these are going to cancel. So it's going to be omega b squared times RB. And then this is going to be 16 point, around 16.6 squared times 0.06. And I got like 16.5 meters per second. So that's kind of the old note. That's why I.
Next, we're going to look at this problem 16-32. 16-32 says the driving belt is twisted so that pulley B rotates in the opposite direction to that of drive wheel A. If A has a constant acceleration of 30 radians per second squared, determine the tangential and normal components of acceleration of a point located at the rim of B when t is 3 seconds starting from rest.
Similar to the last problem, except we're dealing with time rather than rotations. So let's take a look at this. And so this is moving in this direction. Again, because the belts are flipped, this one is moving in this direction. A has a radius of 0.2 meters. And the radius of B is 0.125 meters. And so once again, we're given some information at A, so might as well start with it. We're given that alpha A is 30 radians per second squared. So first look at A. So omega for A, I won't put the subscripts down just to try to keep a little bit uncluttered. Remember, we can use this equation. We can use this because the acceleration constant. Otherwise, we couldn't use it. We'd have to integrate. So plug stuff in. So this is starting at 0. Plus 30 radians per second times 3 seconds. So this comes out to be 90 radians per second. So this, again, is after 3 seconds. And then, so for B, and so again, there's a couple ways you could do this. You could say the belt velocity, maybe you want to do that first. So the velocity of the belt, we can get that from A, how that's going to be our omega A times our radius of A is going to be our 90 times 0.2. And that's going to be what, 18, huh? That's be 18. And what are we in meters per second? So that's going to be the velocity of the belt. And so again, that means that the belt is going to come down, say like this, so the velocity, not a very good picture, but the velocity of the belt is going around in this direction. So it's going to be that speed. So then we can work backwards and say the velocity of the belt for B is going to be equal to the velocity, angular velocity of B times the radius of B. And that's going to be 18 meters per second. Omega B times, and the radius of B is 0.125. So omega B is around 144 radians per second. And the same thing, we could find the acceleration of B. If we first find the acceleration of the belt, same thing as before, the acceleration of the belt is going to be, we know omega A times the radius of A, and that's going to be 30 radians per second times 0.2 meters. And that comes out to be 6 meters per second squared. And then, so then we can go, the acceleration of the belt is going to be equal to alpha B, radius of B, and that's going to be alpha B times 0.125. And that's 48. Angular acceleration B is 48 radians per second squared. So now we have everything that we need to know about B. We can just start plugging numbers in. So we can say the velocity, that say the tangential velocity of B is going to be omega B times the radius of B. Just move that up a little bit. And that's going to be our 144, 0.125. That's going to be 18 meters per second. I guess we didn't really even have to calculate that, did we? Because the belt goes right around B, so it would be the same as the belt velocity. Let me just note that. And then the tangential acceleration of B, alpha B, RB, is going to be 48 times the radius of 125, which is 6 meters per second. And so actually that was also the same as belt acceleration. And then the normal acceleration of B is going to be the velocity of B squared times rho, and that's going to be 18 squared divided by 0.125, and it looks like it's around 2592 meters per second squared. So if you want to find the total velocity at B, you have to take the square root of AT squared plus AN squared. And you can see that that one term is really going to dominate, huh? So we probably don't even need to calculate that, but you can see that's going to be 2592 meters per second squared. Any questions on any of that? Pretty much just a matter of